Team Tuesday!
Team Tuesday! Thanks, David. Today we're talking about the difference between the tools in our toolbox, internalizing them, and applying them with our heart to design and help build concrete structures. And I say it jokingly, but you know, all engineers want to design structures as a box, a short box with thick walls. That's what we want to do. That is the easiest structure. But then you got those dang architects who who come up with these amazing, or you just have the ambient environment. When you go from New Jersey to Minnesota to California, you have a lot of variations in your environment, like seismic loads, wind loads, snow loads, rain loads, that we have to design for. So unfortunately, designing a box, I think actually designing a short box, like a 4-foot tall house with 1 foot thick walls, perfect.
You know, John, one of the mantras of engineers is they can do for $1 what any fool can do for $2. So, you know, let's do those creative things. Let's work with those architects. They create these lovely, beautiful challenges for us to work for.
And that's why it's so important for us to have this conversation today, because as a junior engineer, you have to internalize the basics. You have to fall in love with staring at figures like this, understanding it more than just a representation of the equations, and getting the homework and the exams done.
That's right. I mean, you know, building a building is not a 10-point homework problem.
But it's important to do that.
But it's important as a learning tool, but you know, when you're building real structures, it has to be right.
Amen. So
it has to be right.
Let's dive into it. We've got a great conversation coming up, and it's all based on reinforced concrete design.
Yep.
Ready?
Ready.
We're talking about a rudimentary drawing of a reinforced concrete beam. We only got a few seconds left.
Okay.
But my thing was, I had professors who told me if we didn't balance, you know, this equation, the entire drawing was going to fly off the paper because it wasn't balanced. My argument was that's bullshit. Sorry. What happens if we don't balance the equations and we use those values in a design?
Well, I'm not sure I know exactly the answer. The idea of balanced design is we want to balance the tension on the tension fiber with the compression stresses in the upper portion. And the concept of that is if a beam in a building, say, fails, we want it to fail in tension because we can see that. You can see a little crack form. We all know compression, we load a cylinder, when it fails, kaboom! So we don't want that. We don't want a beam kabooming in compression. We want to see that little tiny crack in tension so that we know something's going on. So that's the general word description of balanced design.
What happens if it's not balanced then?
If it's not balanced, if we're carrying, if the greater, we want a little less, we want the tension to fail first.
Right.
We want the tension capacity to be slightly below balance.
Right, and if it's all on the compression side, then we could have a catastrophic failure.
Yeah.
And that was my point. And it took me years to truly understand it, and how this relates back to that strain diagram that shows you the tension failure versus transition versus compression.
Right.
Because I kept thinking, well, if I don't balance it, it's going to fly off the paper.
Yeah.
I'm an engineer, I'm a literal person, and I know that I thought it was ridiculous, but the connection wasn't there that, hey, if you don't balance this, and you start using these values, bad things can happen.
Obviously, you know, we don't want way more on the tension side, and want way more on the compression side, so we want sort of balance. We don't want exact balance.
Hey. We're talking about equations here and a 300 level course. Balance, but no, you're right, that there is a factor of safety there. And you know, the biggest thing is with these equations, we're trying to represent the physical world.
Right.
And that's a very hard thing to do.
Yeah. You know, design is about thinking about what might go wrong and planning for it not to. That's what really design is about. So we want to think about what is a possible failure mode, and in our design we want to make sure that doesn't happen.
Well, and then we use the already existing information from like ACI 318, you know, the UBC, the IBC, ASCE,
Right.
to determine if our structure or our concrete element is within that tension zone. So we know that the possibility of failure exists.
Right.
But based on that, we play with the geometry, the strength, the steel to get that kind of balance so that when it does fail, we predict how it fails in that tension zone.
Exactly. I mean, if we look at this equation, this is a force couple, right?
Right.
We're trying to balance a force
Totally.
couple. This is a force, area times strength. This is a force, area times 0.85 times strength.
Sure.
That represents that plastic block.
Right, that's Whitney stress block, and it's all separated
Right.
by that moment arm.
That's right.
That D, which is, you know, your most extreme fiber from your tension zone or your compression zone all the way to the middle of your tension zone.
Right. So we recall that in design we learn the moments on a cross section. Moment is a force couple, so we
Right.
take that force couple and design to carry the moment.
That was the most awesome conversation. I am so glad we did that. So what we just covered there was a lot when we consider the job of an engineer.
Right.
Because as an engineer, what David said, well, it's kind of balanced. And what he's driving to is an engineer has to take these equations, their experience, and make judgment calls with design, because buildings are not just square boxes. If we could, engineers would make walls 2 foot thick and buildings maybe 12 feet tall, maybe 15 feet tall, and just really long. You never have to worry about them toppling over.
Yeah.
But then those dang architects.
Yeah. Well, you hear the mantra that the load is the load, and maybe that's right. I mean,
Sure.
we get surprises. I mean, you know,
Oh, totally.
we get loads maybe we weren't expecting. So, but the load is pretty locked down. So, but you know, then we move to stress strain. I mean, I'm a stress strain guy, right? We move to stress strain. Is this stress block exactly what's going to happen in the beam? I mean, are we going to be exactly at the ultimate on the outside fiber and then plastically create this stress block? Maybe. I mean, it's an approximation. Is it a bad approximation? No, it's probably a pretty good approximation. Is it an approximation? Yes, it's an approximation. And that's what design, as you say, that's what design is about. We have to use our guidelines, we have to use our basic concepts, but we have to use our brain, and we have to use our heart.
Oh.
You know, we design with our brain, we finish with our heart. Our job, we're civil engineers, our job is to protect people.
Right.
That's the heart.
Well, and that's our oath. But I mean, the impetus of this talk, which came from absolutely, I mean, that was just the air. I mean, this has been a beautiful talk, is, I mean, what engineering really is. I mean, as engineers, our basic mission is to solve problems.
Solve problems, civils protect people.
This is a tool in our toolbox.
It's a tool.
And it is so important for those junior engineers like Whitney who are taking this reinforced, I don't care whose textbook you're using, but to get this tool in their toolbox and internalize it here so that when they get to the industry, if I only knew that when I was taking this class, not only the first time, but the second time. I truly understood that the third time when I was working for Mr. B and doing structural design, how important these basic concepts are to somebody who is a basic problem solver. So thanks a lot for joining us. We had a great time talking about this. If you have any questions about the concepts behind design and being an engineer and this and that, please let us know. Like, subscribe, go concrete.
Beat asphalt. David out.
John out.